Okay, guys, good morning. 10 a.m. and we can continue. So now we are sort of at a transition point. So tomorrow I will start discussing magnetism. Enough of this electricity. We've been here almost for 2 months. It's kind of right, enough. All right. And so what we're going to do today. First, I want to discuss a little bit power again. All right, because we discussed that in lectures, but we never spent any time in our recitation classes, right? And then we need to introduce a few mathematical tools, okay, mathematical tool and annotation, which we will desperately need once we enter into the world of magnetism, right? So that's basically the scope of today's class. I thought about maybe started discussing magnetism ahead of a lecture, but then it's not worth of troubles. We will start discussing it tomorrow. Okay, so first about power. Let me say a few words about power. All right, electric power, of course, right? Logic behind of this. So what's the advantage, or actually advantages of using electric power? Why do we use electric power all the time, right? Or most of the time, right? For two main reasons. First, it's easier to transport it over long distances. You can transport it over thousands of kilometers, right? We discussed it in a lecture, right? So, okay, now it's a first reason. Now, once electric energy is in our houses, right? We usually don't use electric form of energy directly. And I told you about only two horrible examples where electric form of energy is used directly, and I don't want to repeat them. Right, you remember in the lecture. So every time we transform electric form of energy in some other forms of energy which we need, we don't use electric energy directly. For example, right, if you want to generate heat, thermal energy, yeah, you use the heater, and the heater works as a transformer which transforms electric form of energy into heat. And bulb generate lights, transforms electric form of energy into light. Then motor transforms electric form of energy into mechanical form of energy, right? So every time we transform electric form of energy in something else. And of course, we cannot transform 100%. We cannot transform all energy into some other forms of energy, right? So how much of energy gets transformed? That's what we can ask. Very important question. But of course, researchers went even one step deeper or further in this question. They don't just ask for how much of energy gets transformed. No, they ask how much of energy gets transformed per unit time, how fast that energy gets transformed, right? And of course, energy per unit time, what is that? It's a power. You remember physics 1, right? You discussed power. Okay, so now let me draw a few diagrams about what I just said, and then a couple of conceptual questions, right? Okay, so as I said, we don't use electric form of energy directly. Every time we transform electric energy, usually we send into some kind of a device, right? Which can be a heater, it can be a bulb, it can be motor, right, and etc. Right, you can come up with more examples, right? Right. So you send into these transformers, into these devices, we can call them transformers. Yeah, they transform, right, energies, and then they transform into other forms of energies, forms of energies. Right. Okay, so that's a diagram. And now, of course, what is power? It's energy per unit time, right? So let me just write down. So, of course, power, it's basically by definition, physics 1, energy per time, right? Okay, and we introduced in the lecture, actually I didn't derive, I just showed that here's the derivation, right? We introduced formulas in three forms. First, Usually we use what? Usually in our problems we have either a resistor or a bulb. These are most typical examples, right? And easier to analyze. And of course, in these cases, for example, in the case of a resistor, um, electric energy gets transformed into thermal energy, into heat, right? And all right, so you have a resistor, you apply potential difference delta V. Of course, as a result, current I will flow through that resistor. So in this case, how can we calculate power dissipated by this resistor? You just take a product of potential difference and current. So that in Ohm's law, we divide them, delta V divided by I, but here we multiply them. Right? So it's one form of this formula. Then if you use Ohm's law, of course, you can rewrite this formula into other forms. First one, the second one, delta V squared over R, right? Sometimes this is more convenient. It depends on what is given, it depends what you need to find. And the last form of this formula, I squared times R. Okay, let me frame them all because we will need them all again. It depends on the situation, which formula is easier to use, more convenient, easier to use, right? Okay, so that's the quick review. And now let's discuss a couple of conceptual questions about this, right? So it's a chapter 28, actually. Let me write that down over here, right? Chapter 28. Okay, and conceptual question. Let's start with conceptual question 5. CQ, conceptual question. And we have two resistors given, right? And we know that the resistance of the first resistor is larger than the resistance of the second one, right? So what is given? R1 is larger than R2. That's given. And we need to compare powers. How they are wired, we will see. There are two situations, right? So we need to compare powers. So which one is larger, P1 or P2, or maybe they equal, right? And so conceptual question 5, in this question, they're connected like this. So let me show. It doesn't matter how much I practice drawing these resistors, and every time I'm not happy. Okay, strictly speaking, they look ugly, my resistors. That's why I told you I usually prefer to use rectangles, like a European form of drawing, right? But here, this is used. Right, so they're connected to the battery in this way, right? So this is delta V, right? Battery. And this is, let's say, R1, and this is R2, right? So we need to compare powers. Which resistor dissipates more power, right? Okay, first of all, we need to, of course, identify how they are connected. And of course, obvious, everyone should see that they are connected in parallel. And of course, everyone should remember the test that you have to run in order to convince yourself or somebody else that they are connected in parallel. Right? If potential difference across elements exactly the same, it doesn't matter what you connect over here, right? It can be more complicated than just a battery. But it doesn't matter if it doesn't matter what you connect, potential difference across elements exactly the same, you can say that elements are connected in parallel. Here you can have bulbs, you can have motors, you can have people, you can have whatever you have, right? If potential difference is exactly the same, you can say that those elements are connected in parallel, right? And of course, in this case, it's correct because point here and point there, they're at the same electric potential because they belong to this a big piece of metal. And you remember, in piece of metal, electric potential is the same, right? So let's say here the same, and then below, of course, this point and this point again, now they belong to that piece of metal, just big piece of metal. And the electric potential is exactly the same. So V minus V, V minus V, of course, electric potential difference is going to be the same, right? So in this case, they're connected in parallel, and of course, delta V1 equals to delta 2 and equals to the potential difference created by the battery, right? Okay, so that's important piece of information. And of course, we know that R1 is larger than R2. So now, based on this information, we should be able to compare power. But before, let's analyze which formula is going to be the best in terms of simplicity of the analysis. Okay, let's start, for example, with the first one. Is it good or not? Delta V times I. Okay, so we just found that potential differences are the same. Great. So we have information about delta V. But what about current? Current, of course, here will be I1, I2, and those currents are not equal, and we don't have any information about those currents. Of course, we can find that information, but in order to do that, in order to find that information about currents, we will have to make one or two additional steps. Again, it's not wrong, it's not bad, right? But it's not the most efficient way of addressing this problem, right? So let's be pragmatic and let's search for the easiest option. Again, you can use that, but first you will have to spend a few steps, some time finding current, maybe using equivalent resistance, then Ohm's law, right? Something like that. It can be done. But I'm pragmatic. I want to find the easiest approach, right? Then, what about the last one? I squared times R. Okay? R, information about R's are given, right? Great. So we have immediately information about resistances. But current, the same story. We don't have immediately information about current. Again, that can be found, but at the expense of additional steps. Okay, so let's put it aside. This formula, delta V squared over R. Information about delta V is given, they are the same, and information about resistances are given. So this formula can be applied immediately without any additional steps. So of course, this is the most effective formula in this situation, in this particular situation, right? So I can write, so it's better to use P equals to delta V squared over R. Again, the other two, not wrong, just slightly more complicated, right? Okay, so now after we decided which formula to use, of course, now let's compare. P1, of course, it will be delta V 1 squared over R1, and P2 equals to delta V 2 squared over R2. Potential differences are the same, so I can erase subscript, right? And potential differences are the same, and since R1 is larger than R2 and resistances are in the denominator, so larger value of R is going to make smaller value of power. So I can draw that P1 is smaller than P2. So the larger value resistor with a larger value is going to generate less heat if they're connected, if these two resistors are connected in parallel. Right? So in this case, a larger value resistor generates less heat. Okay, so that's the first situation. Now, conceptual question 4. Let's use the same resistors, but let's rewire them in a different way. All right. Okay, so I think I should be able to fit it below. So now conceptual question 4. So the same resistor, again, I can write that R1 is larger than R2, but now let's wire them this way. So we have a battery, and then we have these resistors connected like this. Right. So let's label delta V, and here let's say R1 and R2. So now they're connected like this. Of course, everyone sees that these resistors connected in series. But again, which test you have to run in order to convince yourself in that fact? Current must be the same. if current is exactly the same through elements, again, it doesn't matter what you have over there, right? It doesn't matter what you have on that side of the circuit, right? If current is exactly the same through the resistor, because you can, by accident, you can have exactly the same currents in two elements which are far away from each other in the circuit, right? Which are not in series, right? By accident. But in this case, it doesn't matter which battery you connect. It doesn't matter what you have over there. In this case, current through these two resistors is going to be exactly the same, right? So basically, that's the test. Currents are the same under any conditions. It means that these elements are connected, these resistors in this case, are connected in series, right? Okay, so now I can write that in this case, of course, I1 equals to I2 equals to the total current taken from the battery. Okay, if you want to prove, if you want to have proof, come on, we don't have a junction points, and you remember conservation of current without junction points. It doesn't matter where you measure it, current is going to be the same. Okay, so now after this, which formula to use? Again, let's analyze all of them, all these three formulas. Let's start again with the first one, delta V times I. Information about current, yeah, we have, because they're in series, currents are the same. Delta V1 and delta V2. They are not the same in general situation, right? And that information about the potential differences are not available right now. Of course, you can find it. It's not a big deal. Maybe using, again, equivalent resistance, right, and Ohm's law, you can find delta V1 and delta V2, but at the expense of one or two additional steps. But again, we want to be pragmatic, and we want to find the most convenient formula out of these three, right? Okay, so, okay, this is not good because of delta V. Now let's look at this one. R, information about R is given, great, so that information is ready, right? But the same story with delta V. Delta V, again, is not given. Again, that can be found, but why would we waste time and efforts, right, finding that? Maybe there is an easier approach. Okay, the last one, I squared times R. I, information about I is given about current, they're equal, and R's, again, that information is available again. So immediately using this formula, we can come up with the conclusion immediately, right, without additional steps. Okay, so I can write that better to use P equals what, I squared times R. Okay, so now let's write P1 will be I squared times R. Immediately I dropped subscript, you see, because currents are the same. And here P2 equals to I squared times, okay, this is R1 and this is R2. And so since currents are the same, but R1 is larger than R2, and since resistances are upstairs in the numerators, so we can write immediately that P1 is larger. I wanted to write larger, draw smaller. Sorry. All right. So that's P1 is larger than P2. Right. You see, we have exactly the same resistors. Right. And in this case, a larger resistor dissipates less or generate less heat, produce less power, right? Thermal energy per unit time. In this case, larger resistor generates more heat, right? So the same resistor, if you wire it in this way, it generates less heat. In this case, if you wire them like this, it generates more heat, right? Okay, so the goal of this was, play mainly with these formulas, analyze which one is more convenient, right? And again, to refresh the test for devices connected in parallel in series. And in the past, I gave something like this among multiple choice questions on the second midterm exam, or the final, or maybe the final exam. Maybe instead of resistors, you can have bulbs, but again, bulb is effectively a resistor which can also generate light, right? And the situation may be slightly more complicated, but again, approach is similar to this, right? So I just wanted to play with that. Okay, so if you have questions about this, we can discuss. Otherwise, at this point, yeah, it's time to start moving to magnetism, right? It's sort of like a leftover from the previous recitation classes. So, as I said, at this point, it makes sense to start introducing magnetism. But before we do that, we need to refresh a very important mathematical tool and very important notation, because we will need them once we go into the magnetic world. We will need them almost every class. So let's spend the rest of this class discussing that. Okay, so first, in the problems about magnetism, we're going to have some electrical systems, right, which will generate electric field, magnetic field, right, or the big mass. And most of the time, we're going to see some kind of three vectors. And one of them can be, for example, along that direction. One will be, for example, upward. And the third vector will be either out of the board or into the board, right? So every time, okay, not every time, but quite often, we're going to see we will have to draw three-dimensional situations. And almost, okay, quite often, right? Quite often, one of the vectors will be either out of the board or into the board, out of the page and into the page. How can we denote those vectors? Because, yeah, you can try to draw a three-dimensional picture, sort of like a three-dimensional, but it's kind of more complicated. So let's come up with a convention which we need, which we will use to denote vectors pointing into the board and out of the board. I'm sure that in Physics 1 you use it, but by this time plenty of students forget about that, right? Okay, so first, notations. Notation. Notations. So first, if a vector which I wrote is out of the page, is out, okay, out of a page or whiteboard. Of course, I will write page, less to right, right? In that case, we're going to use this symbol. Out of the page, this symbol, basically a circle with the point in the middle. Logic, very simple. Even right now, before I drew it, I imagined that logic. I sort of used that logic. It's like an arrow. Imagine an arrow flying towards you. What are you going to see? You're going to see the tip of that arrow, right? So this is the tip, and the circle is basically the edge of an arrow. So that's what you're going to see if an arrow flies towards you, right? And that's the notation, that's the symbol we use to show a vector pointing out of the page, flying towards you, right? So that's the logic. All right, so it's sort of like an arrow flying towards you, right? Oh, right. And the opposite situation, if a vector is into a page, okay, probably I should frame into the page. In that case, we're going to use this symbol, a circle and the cross in the middle. And logic exactly the same. So imagine an arrow flying away from you. What are you going to see? You're going to see stabilizers of an arrow, right? And of course, the simplest symbol is just a cross, stabilizers, right? And of course, the circle again represents the edge of that arrow, right? So again, if you forget about these notations, just recall an arrow, and it will naturally appear in your head. So it's like an arrow flying away from you. Okay, so that's what we, and these notations will be used almost every class from now on, right? Okay, so now after this, we need to introduce, okay, not introduce. You introduced it in physics 1. Now we just need to refresh it. But again, based on my experience, most of students don't remember how to use it properly. Right, right. And I'm talking about the vector product, right? Vector product. So we used a product of two vectors in the recent past, right? You remember we calculated works done by some electric force as the charge moved, right, from initial point to the final point. You remember that? And we used the scalar product, or we used it also. We called it dot product. Why is it called scalar product? Because as inputs into this product, we have two vectors. As an output of the product, you have a number, scalar. That's why it is called a scalar product, because it generates a number, a scalar, right? Input vectors, output scalar, number. That's why it is called scalar product. Now we need to introduce the vector product, all right? So in this case, as inputs, we have two vectors, and as an output, we have another vector. That's why it is called a vector product, because it generates a vector, right? And yes, sometimes it's called a also cross product, because the symbol cross will be used between two vectors in order to show the cross product. Okay, so now let me write this. Maybe I will put a new bullet and write. So now let's introduce. Okay, not to introduce. You introduced it in physics 1. You remember when you were discussing in physics 1 the idea of torque and the idea of angular momentum. Vector product is basically in the definitions of those quantities, right? Torque, it's a vector product between r and f. R, it's a position vector. F, it's a force. Angular momentum, it's a cross product between r, position vector, and the linear momentum, right? So the same tool, mathematical tool. It's just basically vector product. It's a very, very useful mathematical tool which mathematicians introduced for physicists, so that we can explain some phenomena around us. Very simple, right? So vector, or sometimes it's called a cross product. Okay, so now let me pick two arbitrary vectors and introduce it. So let's assume that we have vector, let's say vector A and vector B, right? Two arbitrary vectors. Okay, so how do we introduce the vector product? So vector product will be, okay, let's say it C equals A cross B. Okay, because of this cross, sometimes this product is called as a cross product. Vector, because as an output you have a vector. C is a vector, right? Okay, so since an output is a vector, of course it has a magnitude and direction. So how can we find magnitude? Magnitude can be found by multiplying magnitude of A, magnitude of B, n times sine of angle between these two vectors. So that's how magnitude can be found. Magnitude, right? Okay, very important point, and where students made lots of mistakes. Finding the correct angle between two vectors. You remember I already mentioned to you when we were discussing scalar product, how can we find the correct angle? You need to position tails of both vectors at the same point. If you do that, or maybe like this, right? So this angle less than 180 degrees is the correct angle, right? It can be like this, right? Sometimes vectors can be, for example, one is here, the other one is there. But you remember property of vectors, a property of a vector. If you preserve its magnitude and direction, you can move this vector anywhere you want. You can position it, for example, here, right? As I told you, you need to position their tails at the same point. And this will give you the correct angle, right? Again, guys, if you need some additional explanation, some clarification, or something not clear, just say it, right? Okay, so in this case, this is the correct angle because the tails of both vectors are at the same point. Okay, so now next step, of course, direction. Direction can be found using a right-hand rule, RHR. I just usually abbreviate it, right-hand rule. And I'm going to call it number 1 because on next class, when we will need to find the direction of the magnetic field produced by the current, we're going to use slightly different right-hand rule. And that rule I'm going to call number 2. It's easier to communicate to students, right? Let's use rule number 1, right-hand rule number 1. So this is number 1, which we use to find the direction of the cross product, right? So this is for a direction. Sorry, left-handed people, right? So most of people are right-handed and left-handed people kind of discriminated. So right-hand rule all the time is used, right? But it's not a big deal. You can easily adjust yourself, right? Okay, so how does this rule works? And lots of troubles, right? So let's practice it. So rule, there are a few right-hand rules which can be used. Let's start with the first one. Okay, so you need to take the first vector in the cross product. Order is very important. Don't change order of the product, because in that case you will get direction, you will flip a direction of vector C. So order is very important. So look at the first vector in the cross product, direction, vector A, all right? So right hand, right? First align your right hand along that direction. So you can align, so like this, right? I don't want to show some wrong signs, right? Okay, so along that direction. So of course you can position your hand like this, along the direction of A, or maybe like this, or like this, right? Or maybe like that. So now, second step, after aligning along the vector A, you need to orient your hand in such a way so you can naturally bend your fingers in the direction of B, in the direction of the second vector in the cross product. So if I try to naturally bend my fingers, if I position my hand like this, and if I try to naturally bend my fingers in the B direction, no, I wouldn't be able, right? I know Thai people in their traditional Thai dancing, right? They can do that, right? But doesn't work for me, right? Unless somebody breaks my fingers, only in that case you can bend them towards B direction, in the B direction. But, or if I position my hand like this, still I cannot naturally bend my fingers in the B direction. So I can do it only if I turn it more and position my hand like this. So you see it's still in the direction of A, but now I can naturally bend my fingers in the direction of B. Then outstretch your thumb in the direction, outstretch your thumb, and that thumb gives you direction of A. Oh, I mean direction of C, sorry, direction of C, right? So in this case, you see, thumb is out of the board, and that's the direction of the cross product, right? So out, it means we need to use dot, right? So this is out, so vector C. Okay, also, you need to remember, by definition, that's how mathematicians introduce, right, in order so that we can explain phenomena around us, right? Vector C cross product all the time must be perpendicular to both of these vectors A and B. If your cross product is not perpendicular to one of these vectors, it means that you found the wrong direction. By definition, vector C must be perpendicular to both A and B. It's just because we found that some phenomena, several phenomena, right, around us, in order to find some directions, we have to apply this, right? So in order to explain what God created, right, so mathematicians created some models, some tools, right? And according to this tool, direction of C is perpendicular to both A and B. So in this case, vectors A and B lies in the plane of this whiteboard. Vector C is can be either into the board or out of the board, right? And then quickly apply right hand rule, and it gives you the correct direction out of the board, right? Okay, so it's a first way, first right hand rule. Now, sometimes people use three fingers, right? I know in high schools, teachers like to use that, and lots of students come to the university using three fingers. So how does this work? Okay, so this index finger, right, is for A, for the first vector. Then these fingers, three, or sometimes they just use one finger, right? I usually use three, right? It's not a big deal. For the second vector in the cross product, for the vector B, and then outstretched thumb for C. Okay, so let's apply it. A that way, so my index finger must be that way. B, you see my three fingers along B, and then outstretched thumb gives me direction of C. So it works equally well. Why I don't use this? Because it looks funny, right? This three fingers. That's the only reason why I don't use. I usually bend my fingers all the time. Okay, so it's the second way, using three fingers. Okay, my professors, when I was in your shoes, right, as an undergrad student, they give me a slightly different approach, slightly different way of applying the first approach. They gave me this sort of approach to find the direction. They told us, guys, look, grab the second vector in the cross product, the second, and move it to the tip of the first one, sort of mentally, right? Or sometimes you can draw sort of dash line, right? So mentally, just to move it like this. Why? Because now you will have a unique direction. First direction along A, and then direction along B. So effectively, you're getting some kind of this direction, right? And now just curl your fingers in that direction, and your outstretched thumb, curl your fingers along that direction, and your outstretched thumb gives you the correct direction. Okay, some students, when I showed them this approach, they find it more comfortable. They find that it's more convenient, right? So it's up to you. You just need to make a decision which approach to use, right? Either that a line along A, then bend towards B, right? Or three fingers, or just mentally move the second vector to the tip of the first vector to create this unique flow, then curl your fingers quickly. So just pick one approach and make yourself comfortable, right? So now we're going to spend pretty much till the rest of the class playing, practicing. But if you're still not comfortable, come to my office hours. It's not a big deal, right? So it's just very, very mechanical approach. You just need to develop a habit, and it's very, very simple, right? Okay, not simple, but it's simple once you get the idea, right? Usually during the normal school classes, right? If a student came to my office, usually within like 5-10 minutes, students would get out of the office feeling quite comfortable, right? But you must practice, because almost every formula from this point are going to have the cross product, and we're going to find cross products almost every class. All right, don't wait till the end of the semester and then panic before the final exam, right? And if you're busy during office hours, shoot me an email and we can meet outside of an office hours, right? Not a big deal. Okay, so now let's look at a few examples. So let's start with something like this. So let's say this is A and this is B. Now let's look at this situation. So what's the direction of the cross product? So again, usually quickly realize that direction of C must be perpendicular to both vectors A and B. A and B lie in this plane, in the plane of the whiteboard. So C can be either out of the board or into the board. If you found in direction is not along this line, it means that your direction is completely wrong. Direction of C must be perpendicular to both of these vectors, right? Okay, so in this case, it's either in or out. So let's apply a right-hand rule to find the correct direction. Okay, so let's use a rule, that the first approach. align your hand along the first vector A. So we're still finding A cross B. So along A, right? Again, you can position your hand like this, right, like that. So if I position my hand like this, I will never be able to bend my fingers in the direction of B. It's this direction out of this line. So no way. Or if I position my hand like this, again, I cannot bend my fingers. So there's only one way. I have to orient my hand like this, right? So in this case, yeah, I can bend my fingers towards along the second vector in the cross product along B. And outstretch your thumb, right? You see, thumb gives us the correct direction, which is out of the board. So out of the board, out is dot. So that's direction of C. Or again, like my professors used to tell me, okay, just grab vector B, right? And you see, you're creating this flow, unique direction. Curl your fingers and your thumb gives you the correct direction. Or three fingers. Again, this is for A, this is for B, and C. A, B, and C. You see, C is out. So you're getting correct direction using any of these methods, right? Okay, then I also want to emphasize on one. Let me erase these green lines. Right, look, but what if, for example, a direction of B vector like this? Will a direction of C be any different? It will be still the same. Look, again, still A cross B, so direction of C will be still out of the board. So then we can ask, what's the difference between the cross product of this and this or that? Magnitude will be different because the angle will be different. So magnitude of vector C will be different for these two situations, but the direction will be still the same. Or even if I pick a B direction, that, let's say this is my B direction, still direction of the cross product will be out of the board, but magnitude, of course, will be different, right? Or if I pick direction of B this way, increase the angle, still direction of C will be out of the board, but magnitude will be different because this angle theta will be different, right? Okay, so first example. Now let me move them around. So let's say, what if direction of A and what direction of B? Okay. Again, let's start with the first approach. And you see now I move my body because I feel like it will be more convenient. And that's, I told you, it's kind of sometimes kind of funny to see the final students during the final exam, because sometimes they move themselves, right, bend and twist their hands, right, in order to find the correct directions of the cross product, right? So align your hand along the first vector A, first vector in the cross product. So I have to do it like this, right? Again, it can be like this, or like that, right? Oh, like that. Then you need to orient your hand in such a way so that you can bend naturally your fingers sort of upward in the direction of B. So it means that I have to position my hand like this. Because if I position like this, again, I wouldn't be able to do it. But in this position, yeah, I can bend my fingers in the direction of B. And then my outstretched thumb gives me direction into the board. Again, C must be perpendicular to both of these vectors. So C must be along this line perpendicular to the whiteboard. So the correct direction is into the board. So into the board, it's a cross, right? Or again, the way my professors used to teach me. So B direction, position vector B over here, again, mentally in your head, in order to create this direction of flow. And so curl your fingers, and outstretched thumb gives you the correct direction. So then what if we have, how much time? Okay, we still have 6 minutes, great. So what if we have this situation? So vector A and what? vector B. I didn't label vector B. So now I turned everything almost by 90 degrees. So what do we have here? A is up, B represented by the dot, out of the page. So B is out of the page. So effectively we have this situation. A is up, B is out. So we have this, right? So first of all, realize again that C, vector C, cross product, must be perpendicular to both of these vectors. So it means that vector C must be perpendicular to this plane. All right? So C can be either that way or this way. So C vector must be along this line. If you get any other directions, it's immediately wrong. So it can be either this way or that way. So now let's apply right-hand rule in order to get the correct direction. So first align your hand along vector A, so it means up, right? Then orient your hand. Now turn your hand so that you can naturally bend your fingers out of the page. B is out of the page. So your fingers, you should be able to bend your fingers out of the page. Again, if I position my hand like this, no way I wouldn't be able to bend my fingers out of the board. So I have to position my hand like this. Right. So in this case, yeah, you can see I'm bending B towards, bending fingers towards along the direction of B, and my thumb gives me this direction, right, perpendicular to both of these vectors. Right? So in this case, C is to the right, so direction of C. Right. Okay, so now let me give you this situation. What if vector A is given by the cross, right? And vector B is to the left. This situation. Again, C must be perpendicular. So it means immediately you have only two directions, right? So these two vectors, A is into the board, B is it's that way. So these two vectors form this horizontal plane. So vector C must be perpendicular. It's either up or down. So there are only two directions. So now apply right-hand rule to get the correct one. Okay, A is into the board, cross into, so I have to position my hand into the board. All right, again, it can be like this, like this, like that. But then you need to orient it properly so that you can bend your fingers to the left. So it can be done only if I position my hand like this. So in this case, you see I can bend my fingers in the direction of B. My thumb gives me the correct direction, up. Right, so in this case, C is up. Okay, let me give you probably the last example. Let me twist everything. So let's say vector A is given by this dot. So let's say this is A. Dot means out of the board. So it means that vector A is towards you. And then B, let's say B points along this weird direction, somewhat downward, down and to the right. So what's the direction of C, cross product? Again, you need to realize what are the possible directions for C. Again, you remember C must be perpendicular to both of these vectors. So A is out of the board, sort of like this, right? You see out of the board. B is downward. Okay, sort of down. So they form this plane. They lie in this plane, tilted plane. So C can be, or cannot can be, must be perpendicular to this plane. So C can be either up, right, that way, or this way, or down. Okay, somewhat down. So C can be along this direction. So that's the correct direction. no, correct line. So C must be along this line. But of course, we don't know, is it this way or that way, right? So now, right hand rule. Okay, let me hold you for half a minute, right? So let's apply it. First, align your hand along the first vector A out of the board. Okay, I feel like, I don't know how should I orient myself, right? That's what is usually funny also on the final exam, when students also struggling to find the correct, orient themselves properly. Damn it, right? So I think it will be better this way, right? So first my hand must point, must be aligned out of the board, like this, right? Yeah. Then I need to orient my hand properly, right? So that I can bend my fingers in this direction. So I have to sort of like tilt my hand like this, right? Yeah. And only then I can bend my fingers towards B, right? So you see? And as a result, you see my thumb, it's somewhat upward and to the left, right? So this is the correct direction for C. So you see, sometimes you have to even move your body, right, in order to get the correct direction. So this will be direction of C. Right. So enough of practicing this, and again, do it by yourself, right? And if you need my help, come over to office hours and we can practice. I can give you plenty of examples, right? And of course, it's better when we in person, right, talk, right? So I can adjust your hands, right? You can adjust your position, right? It's of course much more efficient, right? But that's what we have for now, right? And we'll find a way of correcting if you're making some mistake.